Okay, let's look at multiple linear regression for their diagnostics, transformation, and we will cover something about multi-collinearity as well. As I recall, like when I was interviewed for different companies, I think like the multiple linear regression and the associated problem with those models are the most often asked by those interviewers. Yeah, I remember several of them asking about multi-collinearities and also like variable selection, etc. It's all related to this multiple linear regression. Yeah, so let's get into the material for this week. So we did diagnostics for simple linear regression before, right? We will do something very similar as simple linear regression when we do the diagnostics for multiple linear regression. So we will, if you remember, we would check the patterns of the standardized residuals, but for multiple linear regression, there is certain conditions we have to, it has to met in order to use standardized residual for diagnostics. And an alternative is use a marginal model plots, and we'll talk about this probably in the very end of this chapter. And we would also we did like studied what is leverage points and how to determine if it's a good leverage point or bad by looking at if it's outliers. So outliers are those do not follow the bulk of the data. Yeah, so those are just similar as before, and this is the new thing. Like we will assess the effect of each predictor variables on the response variable, and we will use this called added variable plots for that assessment. And we will also assess the effect of collinearity among the predictor factors. And eventually we would also need to check the assumption of constant error variance. Sorry, this is a typo. I'll correct that when I post the slides. So yeah, well, if the constant error variance does not hold, what we can do about it? Yeah, something similar as before and something new for multiple linear regression. All right, let's do a little bit more of the review for the estimation and all the terms involved in the multiple regression. Again, in matrix format, it's easier to work with matrices when we have like more complicated model. So we have this y, x are the predictors, and this column of 1 corresponding to the intercept, and all these others are the variable corresponding to each of the beta. Well, yeah. So, well, I think I might put this beta wrong, but let me double check and correct it if that's the case. Oh no, it is correct. So each of this beta is p plus 1 length of p plus 1 vector. So each of this beta. Well, let me check that. Well, I suspected this is wrong. It should be. So this whole beta should be a vector of p plus 1. So this should go from beta 0 to beta p instead of you have n of them. Yeah, I need to correct that as well. Sorry about that. Okay. For now, ignore this one. We just use this vector of length p plus 1 for this beta vector. Okay, so we have our model y equals x times beta plus our error term. The error term is correct. We have n corresponding errors to each of the data points we have. We would have our fitted value and with our estimated beta hat. So this beta hat is still it's a least square estimate, but this is for for multiple linear regression. We have a larger X matrix, and the residuals is calculated as your data minus your estimated or fitted values y hat, which is x times beta hat. Okay, and we will go over the leverage points again for multiple regression. Just a reminder that leverage points are the points that have a large influence on the fitted model. So it has like some big effect on the model. And we're interested in the relationship between y and y hat. Y hat is the fitted value equals x times your beta hat. We just plug in this beta hat, this part, and you get h times y. And this h in this whole thing is called H matrix, or sometimes we call it hat matrix, because multiplying y by this hat matrix will give y a hat. So we get y hat when we do h times y. Okay, so h hat matrix, and very similar to simple linear regression, we have this y, so the ith fitted value yi hat equals to this. So it's basically use this the leverage value. So by looking at this, we can see the diagonal of this H matrix is capturing the extent by which the regression model yi hat is attracted by the point yi. So this HII, the leverage, times this YI, it gives you like how much the regression model being attracted by this, by your data point YI. So this is your leverage, and we have the rule of thumb for identifying leverage points. Well, in simple linear regression, we still have this HII greater than 2 times the average of HII, where for simple linear regression, this average value is 2 over n. And for multiple linear regression, when we have p predictors, this average is p plus 1 divided by n. Don't forget, we have this 2 times this whole thing. So if HII is greater than this value, we would say it's a leverage point. Okay, and yeah, that's for the leverage part. And let's look at the residuals. Well, now we compute the residuals in terms of the hat matrix, right? E hat is just y minus y hat. And plug in this h times y for this y hat, we get this, where I is just identity matrix. I minus h times y. And the expected value of this vector of the residuals is 0. And the variance of this vector, E hat, is sigma squared times I minus h. Well, if you are curious about how do we get this, please refer to the text. I didn't put like the theoretical part, like all the math here. It's more important that you know the expected value and the variance for this EI, I mean the conclusion. And for I's residual has variance given by this, but we still use this, the diagonal value from this hat matrix. And we can standardize the residual as this, that where we have this EI hat divided by its by its standard error, which is a square root of this. And normally we do not know this sigma, so we would use this as the sample standard deviation to estimate our sigma. So this is where standardized residual, and this S is the estimate of the sigma. And S can be calculated as this. Yes, this is about the standardized residuals. And again, let's go like kind of a review our outliers. What are outliers? Similarly, we call point being an outlier if the standardized residual is outside -2 and 2 for a small to medium data set. And we enlarge this band to -2, -4 to 4 for a large data set. Because if we still use the -2 to 2 for a large data set, there will be like too many data points will be considered outlier. And this is a rule of thumb to determine the outlier. It's kind of related to like your confidence interval, those related things to determine this band. So yeah, this is how we determine if a data point is an outlier. Well, I have to emphasize that we can only declare a point to be an outlier this way after we have decided that the model we're considering is a valid model. Well, it makes sense, right? If the model you're working on is not really valid, so when you see something is an outlier, which does not follow like the pattern of your model, you see that point being outlier would be not fair, right? You just remember that the model we worked on, we have the assumption that it's a valid model, so that we can see, okay, this and that point is outlier. Okay, and let's look at how do we use the residuals and standardized residuals to diagnose if your model is valid, or see if we can get some insight on how the model is wrong. Yeah, so multiple linear regression is a valid model for the data if the condition, like this one, there's two conditions met. So in text, I would say the conditional mean of y given x is a linear function of x, and the conditional variance is constant. So we say this model is a valid model if these two conditions are met. When a valid model has been fit, the plot of the standardized residual against any predictor or linear combination of the predictors, see the fitted value. So the fitted value is a linear combination of the predictors, right? So the plot of this standard residuals will have a random scatter of plots around the horizontal axis, and it would have constant variance as we look along the horizontal axis. This is, we have checked this before, but there's no particular pattern for the standard residual when we plot it against the predictors or fitted values. Also, we have that a pattern in the plot of standardized residual is an indicator of an invalid model being fit. So we look at the standard residual plot and find if our model is valid or not. Okay, we check if there is any pattern and if the variance are constant. Okay, let's see how do we use these residual patterns. Well, the standard residual gave direct information on the issue with the model, as we mentioned. If these two conditions is met, so this like the condition that you have to met in order to check your standardized residuals. So this one is saying the expected the condition mean for y would be a function of this linear model. Like this g is a function, and this whole thing inside the bracket is the argument for this function. And the expectation of xi given xj would be a linear function of this xj. So this is saying the distribution of the predictors follow elliptical symmetric distribution. So this is a weaker assumption than saying those predictors are normally distributed. So this is kind of release the condition of this normal, the normality. And if these two conditions are not met, the pattern in the residual plots indicates an incorrect model, but it does not provide direct information on how the model is incorrect. You see what I'm saying? It's so in order to use the plot of standardized residuals to like get a sight of how the model is incorrect, we have to be sure that these two conditions are met. But if these two conditions are not met, we can look at the residual plots. It shows the model is invalid if there is some pattern, but the pattern on the residual plots do not give us direct information on how the model is wrong. I have some examples with some generated data to show why this is the case. Just kind of prove you cannot like directly use the residual plots without any thinking. So let's look at the first condition where this this expectation of y when s is given is a function of this linear model. So when you simulated data where the condition does not hold, we know like the data from the data we generated, this is not the case. So it's generated from elliptical distribution with standard normal errors and the mean function. We use the mean function to produce y as this function. So clearly this thing is not a linear relationship as this. So we have this G1, this absolute value of this x1, and we have a function G2 with respect to x2. So clearly this is not the case. And this is how how we generate the data. And so we have that the first condition does not hold. Right. And let's look at the data. So here is a scatter plot of scatter plot matrix. And we can just focus on this common symmetric. So let's just look at this one. And the two predictors, the two predictor variable have like low correlation. So there's no correlation for this two variables. and there is not a non-linear relationship between them. So there's no linear or non-linear relationship between x1 and x2. So residuals, if we like look at like how we plot the standardized residuals to find if they have constant variance or not, it shows, well, it's kind of like a fan shape. It's non-constant variance. So the errors, well, so when we generate the data, the errors were generated with constant variance. And when we plot it here, it shows clearly non-constant variance because the first condition does not hold. All we can see by looking at this is that the model is misspecified. But we cannot tell what is the reason. You cannot just say because of the variance is non-constant. So in the multiple linear regression, you cannot directly use the same thing that we used for simple linear regression. Because we have that two conditions, it has to met. So the second condition is that the expectation of xi given xj is a linear function of this xj. Well, I generate a data by this relation, and where this expectation of x2 given x1 is the sign of x1. So, and the error has standard normal distribution. So in this case, this is clearly saying this condition is not. And if we plot the residual, oh sorry, this is just showing you the data, like the y and x1 and x2, and what their relations look like. Well, it shows very, very clearly non-linear relationship between the predictor values. And if we look at the residuals, we'll consider this one. The normal interpretation for this shape is that we need a non-linear term of x1 in the model. However, this is not the case. Well, it shows like this because it's because that the predictors between the predictors x1 and x2 have a nonlinear relationship. So this is causing this thing. Normally, if we look at this standard residual plot, we would say, okay, we need a nonlinear term for x1. Well, that's not the case for this multiple linear regression. So again, in this case, we know the model is wrong, but we cannot directly declare, as before, saying we need a nonlinear term for with respect to x1 to include in the model, because the second condition is not met. So when you look at the diagnostics of your multiple regression model, you have to be really careful. Okay, let's look at, this is kind of a new tool for us. It's called added variable plots. We can use this added variable plots to visually assess the effect of each predictor after we have adjusted for the effects of others. You will see this maybe more clearly when we really show the plots. And our current regression model is this one, which we are familiar. Yeah, we are familiarized with this model. I suppose we are considering the addition, like taking an additional variable z as our predictor for y. So we will have this new this new model by adding this predictor z. Well, maybe it's easier. Well, anyway, yeah. This is like x times beta and z times alpha. And we're interested in estimating this alpha. So this alpha is the regression coefficients measuring the effect of this predictor z on your response y. Having already estimated the effect of x on y. So we want to get this alpha after we have like adjusted the effect of x on y. So how we do this added variable plots? Well, we will plot the residual from the original model on the vertical axis. Original model is this one. So we plot residual from this one on our vertical axis, which is on y-axis, and the residual from this model on horizontal axis. Look at this model. We regress z on x, which this one, like the residual from this one, will give us the part of z not predicted by x. Like the residual is what is not like explained or modeled by your by the predictor here, x. Well, if you think about this one, we have a residual from y equals x times beta plus r on y-axis, and we have the residual from this one on x-axis. So it will give us the part of y that's not predicted by x against the part of z not predicted by x. So basically we plotted what is left over from this two model y and x axis. And it will give us the effect of x after it's removed from both axes. So we remove the effect of x on the y-axis because we plotted the residual, and on the horizontal axis, well, let's see x-axis. Okay. Anyway, so the residual from the original model after we remove the effect of x, we plotted on the vertical axis, and the residual for this z after we remove the effect of x on horizontal axis. So if the added variable plot is the valid model for the data, then the added variable plot will produce points randomly scattered around a line through the origin with slope alpha hat. So basically, those added variable plots will show you how much effect is left for this z to explain y. And the slope is actually the slope from the added variable plot, like if you fit a linear model for the on the added variable plot. That line, the slope of that line is actually an estimate of alpha. Let's take a look at the example here. Yeah, so this is a model, yeah, the data that we worked before is the NYC +1 data. So it shows you the scatter plot here for our response variable versus each of the predictors. So we have 4 predictors, and we made a scatter plot for each of them versus our response variable. Well, the problem here is that we are ignoring other predictors when we do like this single plot. We are ignoring decoy surveys and whether it's on the east or west of whichever avenue, Fifth Avenue. Yeah, so that's the problem if we do like this, each single plot. And now we do added variable plot. So, well, let's take a look at this first. So basically on the y-axis is the residual of the price regress on like all other predictors beside food. And on the x-axis is the residual from the model of food regress on all other three variables like decor, service, and waste. So this is one residual after removing the effect of all these three predictors. And this is the residual for the food after remove effect of the three predictors effect. And we can see that in this, well, all similarly we plotted for each of your predictors. And we can see that in the service plot, well, this service plot, it's a totally horizontal line, right? That means the service add very little to the prediction of y. So that's saying it's not really significantly statistical significance for this service coefficient. While others have added some effect to predicting price after adjusting for other predictors. So basically, if it's a horizontal line, that means this predictor is not contributing much. If it has a larger slope, that means this is an important predictor for your multiple regression model. East added a bit, even though it's not much, and decor and the food has added quite some of the effect in predicting the price. Well, I think we will go to a lab to have a better understanding of what we have talked. So this is our lab for this chapter or for this week. And yeah, I figured out it's better that I just go through the file after meeting our markdown file. Because when I look at the videos that we recorded before, well, the section of the code is only on the up right corner, which is well, it's better we just look at this. It's cleaner and easier to look. So the first access. The first access we have is to fit a model and look at, yes, here we fitted a model for the defective products as on the temperature, density, and rate. So the first thing we do, we always do a scatter matrix plot by doing this pairs on this response variable, regress, now this theta, on these three predictors. It will give you this scatter plot matrices. Yeah. Well, it shows the defective have sort of linear relationship with all three of them. And this is how we do this linear model. Well, I still use the same like exercise for the transformation. We will we'll talk about transformation after we talk about the theory. But for now, let's just focus on building a multiple regression model and also do an added variable plot. Yeah, so this is how we do this multiple linear regression, and we get the summary of it, and we check the standard residuals by plotting the standardized residual. This is how I extract the standard residual from your model. And you plot it against each of your predictors and also the fitted value. Well, it looks okay, right? Well, yeah, this part let's ignore for a second. And in this very last part, we did added variable plot for each variable, which you use this AV plots, which is added variable plots, and you put your model. Well, this model I put here is after the transformation where we did, but this is how you do the added variable plots. And looking at this to look at how each of your predictor is contributing to predicting your response. Well, I'm just showing you how to get this added variable plots. And let's go to the transformation part. Yeah, so when we find that there is something wrong, like by looking at the residual plots, we would have to do something for it. Or like when we figure out, yeah, when we figure out it's not a really linear model, yeah, we will do some transformations to help us to get it to linear. So similarly as before, we use transformations to overcome problems for nonlinearity. And also we use this, remember we use log-log as log-log transformation to estimate percentage effects. So there are, so in before we have two general methods for transforming Y and or your predictors. We can use inverse response plots, and we can use box plot procedures to get like an estimate of lambda. But you will see that soon. And we learned both from simple linear regression. We will just do a quick review. Oops, not that quick. So inverse response plots is trying to get the function g on this linear model. So this y have this relationship of it's a function of this linear model. And g is an unknown that we want to estimate with this inverse response plot. So basically we are transforming this y in order to have a linear relationship. So we're estimating this g inverse by plotting y on the horizontal axis and y hat on the vertical axis, where this y hat is just your like estimated or fitted value. Well, Box-Cox transformation, well, again, this is the formula. To do the transformation, this is the lambda parameter for the transformation. Remember, when lambda equal to 0, it's corresponding to a log transformation. But when lambda not equal to 0, it's kind of the power to y, and you have this complicated transformation. Well, this method uses the idea that for some value of the lambda, the transformed version of y, which is this phi or psi of a function of y and lambda. So this value is the transformed version of y. So it's based on the idea that this transformed y is normally distributed. So we use Box-Cox to find the lambda that maximizes the log likelihood function for this. This is the idea behind like this Box-Cox transformation. But you remember we just use our function to get an estimate of lambda. Yeah, let's go back to the defective rate example. Sorry. Let's go to the, well, here we go. We have this first model fitted, and we made a plot to check the standardized residual, and we figured it seemed okay, but if we plot, so this residuals, this plot looks all right, I would say. This right, we will do, we will plot the fitted value on the x-axis and the defective on the y-axis. So the fitted value is this model extracted from your model 1, which is this model. This model, we get the fitted values and we plot it on the x-axis. Remember, this first one is your x-axis, and this is the defective, like your response on y-axis. Oh yes, I meant to, kind of forget what I'm doing here. So I meant to check the relationship between your fitted value and your y versus y hat. So I made a plot here. So then we would add a linear regression line and also a quadratic line to see, to kind of fit a model between this y and the y hat. So this is y, and this is y hat, and we fit a model and add it to this plot. So this is this straight line. And we also did a quadratic fitting by doing this this model, like adding this quadratic term to the model, and adding this line to this plot. So basically, you get a sequence of data on x-axis, and you predict to use this model to get each point on the y value. So it gives you a line. Yeah, you might have to remember this. Like how do you do the prediction? So this is one command to get the value on the y value for this line, and this is your x value. So this inverse response plot is indicating that we should transform y because this linear line seems does not fit so well when we compare the y and y hat. So let's do inverse response plot with this function. Well, this function is from this library. So what we do, we just do this inverse response plot with this model, and it will give you the estimate for this the power to y. So yeah, it's just the lambda, where I should say y hat equal to y to the power of lambda. Well, it checked lambda being -1, 0, and 1, and figured out this lambda being 0.44 gave us the best fit. And if you look at the output from this function, the first one is the best estimate for the lambda hat. The best estimate for lambda, which is your lambda hat. So this is how you use this inverse response plot to get this y to the power of lambda hat. And if we look at the box-Cox function to see like what transformation it suggests, well, box-Cox function is from this library, mass library, and this is how we do box-Cox. And we supply a range of lambda, but here it's kind of cheating because we kind of know this lambda is between 0.3 and 0.6, but normally you might give a larger range and then shrink it to show a better plot for you. So for this case, it gave us the lambda estimate, the best lambda estimate, which gave us the maximum log likelihood. And the lambda hat being around 0.45, very similar to what the inverse response plot is showing us. So, well, we run up a little bit for that lambda hat. We use 0.5 instead. So now let's do a transformation for this y being y to the power of 0.5, basically square root of y. And we again did a scatter matrix plot and see the linear relationship is much more clear this time. If you do this y across the y versus each of this is versus temperature, this is versus the density, y versus density, and y square root of y versus the root. They look much more linear, right? And now we create a new model for this. And look at the summary and we check the standardized residuals, they all look okay. And now let's plot again y from the new y, square root of y, versus the y hat. Now it looks like a really clearly linear relationship between y, square root of y with y hat. And again, well, this is the added variable plot for the second model. Yeah, we will check that after we check this new y versus y hat. Oh, by the way, so when you fit this model, you might realize, well, the first model, if you look closely, you might realize, oh, okay, many of them or none of them are really significantly, statistical significance to the model. Well, the reason behind that is they are actually very much linearly correlated, these predictors. So that causes some problem. But this is not the focus for this example. We will talk about that later. I'm just showing you like if we do a transformation, transformation of y, we can increase the performance of the model. But this one has the problem of multiple linearity when we have these predictors being really highly correlated. But for this example, when we do the transformation, it shows better model to us. Yeah, we'll talk about the multiple linearity later. Okay, what if we need to transform both the response and predictors? We have encountered this scenario when we do simple linear regression, right? So again, if some of the predictors and the response variable are highly skewed and transformation necessary and desirable, we have two approaches for this situation. We can do approach one where we transform the predictors first so that the distribution is kind of jointly normal. And one way to do this is to use the Box-Cox multivariate transform. Note we have multiple predictors now. So we will learn how to do the box plots multi-layer transformation. And after we do the transformation on predictors, we do an inverse response plot with the transformed predictors to decide the transformation for y. So two steps. Or we can use this approach too, which seems simpler. We transform everything at y with all your predictors. Use a multivariate box plots method. We will illustrate both with example. Or it's an extended version of the magazine ad revenue data. They will determine the proper transformations for each of the variable. Let's look at our R lab for exercise 2. So we have the data here, magazines.csv, read it in. Again, plot scatter plot matrix here. And well, for this one, looks like all the data clumps together in this corner. For this kind of indicator, I'll use a log transformation to kind of extend them to a larger range. But this is just by looking at the scatter plot. But let's do a power transform. Yeah, this is actually a box plots transformation, but the function is called power transform. Let's see what this function suggests us. How do we do the transformation for all these three predictors? Well, by the way, we are showing the approach 1, where we first transform the predictors by this multivariate box plots. So we do this power transform, we say bind all these three predictors and do a summary of them, look at the estimated power for each of these predictors. They are pretty close to 0, right? Like the power equals to 0 would correspond to a log transformation. Yeah, so when the data is, I mentioned when the data is scrunched together towards 0, log is the way to go. So this makes sense. Well, this power transform suggests I do log for all of them. So this is how I do that. And I also did, the second step for the approach 1 is that we do an inverse response plot to see with the transformed predictors, what do we do for the one, for the ad revenue, yeah. And this lambda suggests, this inverse response plot suggests a lambda hat being 0.23. This black one fit this pretty good, right? Lambda hat being 0.23. And you can use this, like you can do y to the power of 0.23. Or the book gave an argument that lambda equal to 0 is adequate. Lambda equal to 0 is all right. But I think then more importantly, probably the log transformation gave us this percentage effect interpretation. So I choose to use this log for y and for x. So yeah, this is how we do the transformation for both y and x for approach 1, and for approach 2, let's just use power transform on all your response variable and your predictors. Look at here, I added this y variable here for this power transform, and it gave us the estimate here, all close to 0. So, well, it's agreed with the approach 1. Yeah, let's do a pairs function to do a scatter matrix plot. And right now it looks much better. And well, after log transformation, we can tell among those predictors, we do not have this collinearity problem. But this y, the new y you have a much better linear relationship between for all of them. I mean, comparing to the untransformed version of the model, right? Well, let's do this model and do a summary. The model is pretty good and it is pretty high R squared. And we check the standardized residual. Looks all right. But they are pretty horizontal. Like if we look at the pattern of the residuals, they're okay. And if we do yeah, this is how you do residual plots. Just show the residual plots like against each of your new variable and also the the residual versus the fitted value. Yeah, the residual plots, if this is just showing you a residual plot on this is after transform the model. But if you do the residual plots for your original model where we did not do any transformation, the residual is not that good. It shows some pattern and all clumped together. That shows our transformation is working. And if we do our inverse response plots on the new model, the transformed, it shows a clearly straight line. They're very much linear. It's an indicator that this is a very good model already after the transformation. Now, if we want to interpret the model, after we decide the model is valid, well, the coefficients, because both y and x are log-log transformed, so the interpretation for the log-log would hold. So it would increase 1.03% in, well, let's, yeah, so this is 1.03% increase in avenue if we increase 1% in revenue, ad revenue, if we increase this ad pages by 1%. And we would increase 0.56% in ad revenue for a 1% increase in this sub revenue. Well, this is the interpretation when we have log-log transformation. This is quite important. And again, let's do a added variable plot with the transform model. It shows us like this, all of them are adding some effect to predicting all of this transformed predictors, adding contributes quite a bit for this first two. And for the last one, it contributes, but not that much, right? Because the slope for this predictor is not that big. And if you think about it, you compare the slope with the statistical significance of the variable. See, the first two are really highly significant to the model. And the last one, it got a small slope, and the p-value for this, for the estimates of this coefficient is not significant if we're testing at 0.05 level, but it will be significant if we test at 0.1 level, right? It has some connection. Well, okay, this is for the transformation. We will stop here for now.